Works with home now where I can't do lab one disaster recovery.
That's the age.
I'm always able to until now.
No, yeah.
Why?
Math does not do. It does not like you. You know that. How did you do your 2.5?
What's super about?
Sharp.
I maybe have that's great now. I haven't done that.
All right, guys, let's get started. Today is Thursday. We're going to do lab. Just going to go over RSA today. So I have a nice little script. Hopefully we'll spend the whole class just going over. So I introduced RSA on Tuesday and last week also. We went over the algorithm. We've done some problems by hand, right, on how to compute things. And so today we're just going to try to follow that same logic. So you should understand the logic now. And we're just going to implement it in Python. This is from scratch. So what that means is, no libraries of any kind. Later on, we're going to look at PyCryptoDome, or if you're using OpenSSL, we're using some kind of built-in library. OpenSSL would be the preferred mechanism or tool to use RSA. But in this example, the goal is to understand the algorithm as much as possible. And you already do, right? So you already understand, hopefully from lecture on Tuesday, a lot of the steps of how it works. And today we're just going to see it in action. Pay attention to this script. This is one of the scripts that will be in the practical exam. So I will use it to encrypt something, right? So make sure although the goal is, there's two goals here: to understand how the algorithm works, to see it in action, but also to know how to use just the functions and everything, right? So for the exam, I don't usually ask you to write code from scratch. You can use just the scripts that we've used in class, but you do need to understand how it works, like the workflow of it, right? So that's basically the idea. Okay, so let's kind of, and I've been grading your assignments, I think, or sorry, your exams. I think I'm like halfway, so a little bit more than that. So you can check your grades. So let's go into today's lab. It should be a fun one, I think. We have a homework assignment due tonight. What would it? Oh, what is it? It's the XOR?
XOR.
CBC, right? Yeah.
Yeah.
Okay, great. And then today, this assignment. So we did the first two problems last Thursday. Today we're doing the last two problems of the four. And then so this homework would be due a week from today. Okay. So let's take a look here. So I'm basically in this module, RSA, the basics of it. Whoops. So we should be RSA homework. There we go. So we'll reread this. All right. So last week we went over problem 1. Problem 2, we've done both in Python and by hand, I think. And then now today, we're going to focus on problem 3, really. And then problem 4, you guys can do on your own. So problem 4. So let's go over, and there's nothing else in here. So problem 4, using the code from problem 3, plus any symmetric encryption approach, send a message to your partner and achieve confidentiality. This time you must exchange the symmetric key securely, right? And so you can finally do the entire encryption of confidentiality from one, place in the world to another place in the world, because you have everything that you need now. Asymmetric encryption for key exchange, and then you can use whatever you want. OpenSSL is fine, and use that key. Got it? So that's something that you will do on your own. You should understand basically how this works by now. All right. And then so today the focus is problem 3. We'll download the script from GitHub, and then we'll just go over line by line and kind of understand. But it's basically what we covered on Tuesday, just in there. And so you'll see certain things that I mentioned, like the EEA algorithm, etc. You'll see those in action and they're implemented from scratch. So problem 3, now that you have completed problem 2, try using a more advanced implementation. Because of the complexity of the RSA algorithm, some functions are provided for you. Okay, so for this problem, you will need the source code provided in Blackboard or on GitHub. I think it's also on Blackboard. You need to write the generate key. So I'll go over all of this with you guys. Generate function, and then you need to use all functions available to generate the prime numbers, generate the keys, and encrypt and decrypt the message. So this time we'll have like a proper prime number generation function and all those things, and you'll see it gets pretty big, right? So that's basically the goal. All right, so yeah, so that's the problem. So let me actually, before I forget, I'm going to create the assignment for this. So you can see there is no assignment link here, so I haven't created that. Right? So create the assignment link. All right, so I'm just going to call this homework RSA intro. I guess this was the first RSA homework, right? And this is going to be due, today's the 3rd, so it's going to be on the 10th, 10 p.m. Open now. And it'll stay open until Sunday, the 13th. Complete the 4 problems when the attached Word document. Okay. All right. So hopefully that's clear enough. Let me know if you have questions. So that's the link, and you can submit your report as we usually do. Okay. So that's in there now. There it is. Okay, should be open. So now let's go to, we are sharing the screen, I believe. So recording. Go to the virtual machine. Log in. Okay. And like I said, we're just going to go over the code, kind of play with it a little bit. So I'm going to need to download it first. So I'm going to go to the GitHub. I'll show you where it should be. So let's go to just want to make sure I don't have any. This one. All right, it's just that way I'm not going to make a mistake here. All right, so let's go. So the script in question is in the GitHub repo. You should know where that is, at this point. So, taking a while there. Okay. No, there it is. I do have it. Oh, there it is. Okay, so I'm going to go to the GitHub. It's really slow, apparently. All right, repos. And just look for cryptography. There it is. All right, and this one will be RSA, should be in here. I think I have two scripts in there. Like one is kind of missing some things, and then the other one isn't. I have some additional things like convert hex to decimal, things like this. These are just little functions to convert, a key, for instance, right, to something that's not a byte array, and so we might come back to it at some point. But for now, the focus is these two scripts. So I believe it should be RSA full code. Yeah, it's this one. So it should say import pickle here. So it should have the pickle functionality that we talked about. Remember, you'll have to use this because in cryptography, we're using byte arrays, right? We're generating these byte arrays as when we encrypt, when we have keys, and you'll need to exchange the data, right, with your classmate. Okay, so that's basically the plan. So I'm gonna go ahead and just click on download raw file. So hopefully it'll start downloading. Okay. Let's see. All right, so it should be called RSA full code. So maybe it's in the downloads here somewhere. Yeah, RSA full code. There it is. So I'm just going to move it to the desktop. And we have ITS 350 full 2024. And in here, I guess I had an RSA already. Okay, Tora. Yeah, I'm just going to add it in. Everyone with me? So that's basically the script that you need. So the goal today, we're just going to go over this, describe everything about it. Okay, here. All right. So I'm gonna, there's like a main section, and then the main section makes a call to several functions, right? And so that's kind of what we're going to debug, if you will, go over all the lines of code, etc. All right, so I have this now, so I'm going to proceed to just use I want to use the terminal, ls-l, cd desktop, and then ls-l, cd its 350 fall 2024 clear cd RSA here. All right, so we have our RSA full code, right? And same approach. So we're gonna debug it here. Say, all right, so here we are. So this is your script. Let's you can see it's got everything in there. Very, very interesting thing. So we're gonna talk about it. So you can see it's not that long, and it's a full implementation, a simple but yet ever more complex implementation of RSA. Okay. Keep in mind there will be different versions of this, right? Some, people will try different techniques. This one does have a small difference from what we did by hand on Tuesday that I will emphasize, for the computation of things, but otherwise it's pretty similar. Okay. So let's go over here so you can see. I'm going to start at this area here. So before that, I just have a whole bunch of functions that we're going to need for various tasks. So this is the part that, you guys have to play with. So as you can see here, what we did on Tuesday is pretty much what we're doing today. So what was RSA? We had several steps, right? So the first step was to do what? Find two prime numbers, P and Q, such that, they are different, right? So as you can see here now, we have this function get prime, right? So this function get prime, we'll look at in a second, but it generates a number, randomly, and then it checks if it's a prime. And the key thing is that it's going to generate a number of a specific size. You see this seed size? So this seed size is a variable that we're going to define. So what I want you to do in the assignment is I want you to, run this code with a seed of 256, then run it with a seed of 512, then run it with a seed of 1024, 2048, 4096, and so on. All right. And what's the point of that? The point of that is that you will see that eventually, actually, it starts to really slow down. It's, very intensive. Obviously, this is not OpenSSL will be much faster because it's written in C and it's very optimized. So you have to keep that in mind. But in general, this is still a nice experiment to compare the different key sizes and their impact. All right. So it's going to slow things down. So that's why if you were doing that Netflix movie, as I've said many times, and you're downloading it and you're using a key of 496, it's going to take you a while for it to download and decrypt, right? So this is mainly just for the key exchange. All right, I will be using the input here, and oops. Okay. Input function is basically to halt the program so that we can just look at specific things. All right, so added the input. So first thing, I'm going to run it. Hopefully it won't break. And I'm just going to generate 2 prime numbers, right? Get prime. We'll run the code and then we'll start digging into all the different functions and just kind of, go from there. All right. And, this is a nice exercise. So let's go ahead and print P and Q and see what they look like. So I'm going to do Control X, Y, enter. Clear here. All right. And I'm going to do Python 3. Right. And there you go. Look at those prime numbers. What do you think? Pretty great, right? So these are prime numbers. Maybe you've never seen a prime number this big. I don't know. All right. But these are prime numbers. And you can try different parameters. Right. So now what we have to do is we have to take P in step 2, P times Q, right, to generate N. And you can see, this is cryptography right here. Okay. So if you were going to break cryptography, right, what would you have? You would have an N that is P times Q. So you would have to factorize that N and find these 2 prime numbers. You find those 2 prime numbers, you break all cryptography. This is the holy grail, right? So many people are worried that some quantum, as I've said many times, quantum computers or whatever, maybe AI could break that N, like figure out some pattern that we humans just can't find. And then if they can grab an N, get this P and Q, like the whole internet stops working. Right? Think about it. If one of you, I always make this joke. If one of you was a researcher and discovered this, what do you think that would happen? What's the easiest solution? If you discovered how to, an algorithm that you take N, right, and you can find P and Q, and you're like, you call someone, you haven't told anyone yet. Yep, I agree with you. That's probably the simplest solution. Otherwise, they might just make you disappear. It's simpler than changing the whole world, right? So it's interesting. So or they'll put you in a bunker forever. Maybe that's like the nice solution. So anyway, yeah. So it's a key. It's very real. This is a very real thing and a very real issue. It's amazing that they haven't broken RSA yet, I guess, or maybe it's just such a great algorithm. Who knows? But anyway, that's the idea, and we'll keep on that theme for a while. Okay. So remember, we will do an exercise where we break RSA a little bit in the future. All right. Anyway, so we saw this. So now, as I said, I want to go over the entire script, right, and just make sure everything works. And then after that, we're going to start going into the individual functions. So the function that I just used, get prime, that's basically this function here. As you can see, this function has no libraries or anything like that. Everything is written from scratch. So you literally, we'll debug this a little bit, but you can see it's based on a lot of principles. Like this would be something called the Miller-Rabin primality test, right? So it just basically checks to see if a number is a prime number. So RSA is made of several other algorithms. Okay, so now let's keep going. So we have a function that generates prime numbers. You know, we can try just for fun, although you will try this on your own, and you have to run the whole thing. So let's see how big that is. 6. Okay. Notice how it hasn't even generated anything yet. You see that? Just give it a minute. Hopefully we'll get something. It's a while, right? So yeah. And like I said, I mean, also Python is not the fastest programming language, so there is that, but you can see that there's a big impact. So anyway, you guys can try this on your own. All right, so let's keep going. So we've got the prime numbers. So now the next step in the RSA algorithm was to calculate n, and then from n we have to find e and d, right? And then once we have those parameters, we can proceed to encrypt. So in this case, I'm going to remove the input from here. Now, if you notice, we're going to try to encrypt several messages. So in the future, you can actually read the data from a text file. You know how to do that already. We went over those functions. Here, I just have a simple plain text message that we're going to try to encrypt. Claude Shannon is the father of cryptography. But I also added the comment that this is where the AES CBC key would go, or something like that, right? So this is pretty important. So for the practical exam, that means I will probably encrypt some message with AES, right? And AES will need a key, and I may use OpenSSL or PyCryptoDome, something like that. And that key, then I would place here possibly, right? I would place that AES key here, and then I would use this code to encrypt it. Do you guys see that? So maybe the only way to find this key will be to break RSA, right? So pay attention to that. So I may, use a quantum computer example, or I may use FactorDB, and I'll show you guys how that process would go. But my point is, in the practical exam, the only way to get this key would be possibly to break RSA, like if you were a hacker, right, and you broke the RSA algorithm. So make a mental note of that. This is usually where I hide the key, and I use this script because I think this is the script where we can actually implement that process of breaking it. Got it? All right, so make a note of that. All right, anyway, so today we'll encrypt both. So for now, let's comment this one out. And instead, let's try to encrypt the message. Claude Shannon is the father of cryptography. All right, so once we have the message, the first thing you're going to do is generate GenRSA. Now, remember, when you do GenRSA, you only do that once, right? And then you would make your public key available, and then you start encrypting things. Remember, with this problem, you're going to work with your classmate, and you need to create a key, send it to them. They need to decrypt it, and then they need to use that key to decrypt some other thing, which would be some secret message, right? That you're trying to send them securely. So now let's take a look at GenRSA. So you can see GenRSA takes P and Q, the two prime numbers, and will generate our E, which is our encryption exponent, our D, which is the decryption exponent, and N. Okay, so these are the same things that we discussed on Tuesday. So I will just, so let's go ahead here. Let's run it first. until this point, and then we'll get into the details. So I'm going to do input just to halt the program, right? So notice this returns ed and n, then I can use the tuple e comma n, that's the public key, d comma n, that's the private key. I can print them individually or together, okay? This is another thing that I may do. I may just hide this in some text file, for instance, and I'll just say public key, right? And during the practical exam, then you'll need to go in, and what would you do if you're breaking RSA? You would go and grab this n, right? Grab it and then break it, factorize it, get P and Q, and then once you have P and Q, boom, you can use this script to decrypt everything. Got it? All right, so we'll do an example of that later. So let's go ahead and run this now further. I think I still have that 4096, so let me definitely change that, because that's going to slow things down. Yeah, so see size 4096 is pretty slow. Let's change it back to 256. Okay. That's why. Right. There we go. So that's a lot of numbers. So these are the two prime numbers, right? These are the prime numbers. These three, I can tell that this is the public key. This is probably D, and this is probably E. No, this is E. So, well, one of these is N. So let's actually look at the code, because I don't. Oh, actually, I can look at my GitHub here. So the first thing we're looking at is the two prime numbers. That's these two here. Okay, then I'm printing. I guess I printed the. I may have some print statements in the function. So according to this, we should print the two prime numbers, and then we should print, okay, yeah, here, yeah. So we are printing N first, then E, then D, and then, the public and private key together, right? So N should be the first, then E, and then D. Okay. All right, so two prime numbers. So this should be N. That's N. So P times Q. That's N. I encourage you to do that by hand. Mm-hmm. All right, then I have E here. Notice it's 65,537, which I had mentioned this before. Basically, what we were doing is we were picking between 1 and 5 a number, right, that was within that range and was also GCD. With 5, if you think about it, a lot of the time you can just use this number, okay, and it works. Then after that, this should be D, right, D. And then what I have here is the tuple. So this is actually the public key. So one of the things that we will look at later in the semester when we look at OpenSSL is we'll print a public and a private key, and we will try to extract these parameters from the public and the private key, right? So this is your E exponent right here, and this is N over here. It starts at 1384. And then you can see that N is also over here, 1384, as part of the private key. And here is your D exponent, 1, 2, 5, and so on. Pretty big, right? So now think about this operation. You're raising a message to the power of that mod N, right? So pretty big. And actually, these are only 256. They're not even as big as they can be. Any questions? All right, so that's where we are. So we printed the numbers. we know these are for sure prime numbers. Whoops. So now, I have to kill this. I'm going to hit clear. Right? And we can go back to the script. So we're just iterating through it, trying to figure things out. Okay. Let's continue. All right. So we printed everything up until this point. So now I'm going to do an encryption. So I have this function encrypt. As I said, we'll look at these in detail in a second. But I have an encrypt function. It takes plain message, which is Claude Shannon is the father of cryptography. It'll take the E and the N, and it'll produce the cipher. This cipher, as you can see, I've already added the pickle code. So that's already a byte array. So the most convenient thing to do is to save it to take a dump of the cipher in RAM and just send it to a text file. All right, or a file. So remember the idea, we use pickle WB, write bytes, right? And then we're just going to send cipher to file X, which is pickle cipher, right? And then it'll close, and that's, you've created your file. So let's do that. I'm going to add input just to hold the program there. Control X, Y. So if you look, whoops, I only have 2 files in here. Now I'm going to run the script. Okay. Did that. Yeah, I removed it. So now, ls-l, we do have our pickle cipher. So that is basically the message Claude Shannon is the father of cryptography, but encrypted, right? So we can take a look at it, cat pickle. And as you can see, it looks like bytes, basically. Any questions? All right. Now we're going to proceed to take, let's say you're working with your teammate, your classmate, what would you do? That's the key, right? That's the key that you've encrypted. You will send this file via email. Okay? So on. So now, it's not as easy as you think, because you have to use the proper keys, right? Remember that with RSA now, you have Bob and Alice, and each have their own public and private key. Remember that? So you'll have to think about this problem. Whose public key you need to use to encrypt the secret key so that you can achieve perfect confidentiality, okay? So that's one of the challenges that I leave to you. And, you have to think about that. Questions? Clear? All right, perfect. So now, guys over there, any questions? Questions? Yeah. So let's go back to the code, right? So let's say you've sent the file. The file is now at the other, has been received. So now you have to decrypt it, right? We're going to go back in here. Back here. And today I definitely want to give you some time towards the end of class to try to do this, right? I want you to try, because I think you don't realize that it's going to be more confusing than you think. Okay, so there are a few challenges in figuring out which key you have to use. So try it out definitely, today, and let me know if you have any questions, if you don't understand something. All right, so now the file has been received at the other end. Okay, so then we're going to proceed to do that part. So, you got pickle cipher. Remember, now you're going to use pickle, but you're going to do RB, read bytes. So you load the file, and now you have it stored in memory as from pickle cipher. Okay, so this is something we had done before. Okay, and so you can, we have cipher over here, right? So we can, before we decrypt it, actually, let's just take a look at cipher by printing it from the Python program. So I'm going to add an input here. Okay. I'm going to do clear here. And this is what it looks like. Okay. So as you can see, this is basically a list of the encrypted file, or you can see it as a hexadecimal equivalent also. Okay. Now you don't have to worry about the format because you're just saving it. This is how it's stored in memory, right? And so this is how it's stored in memory. And this is how you're writing it basically to the file that you're going to send, right? With Pickle. All right. So, go back to the script. Let's just keep going. All right, so the last part is you have the file now, so I'm going to remove this input, and now you're just going to decrypt it. Remember, we're reading it from a file, so we read it into the variable from pickle cipher. So notice here, I'm invoking this function decrypt. We'll look at that function in a second, but now you're taking from pickle cipher, you're taking the D exponent, and notice that instead of using N, you use P and Q. This is perfectly fine because this is the private key, right? So the private key, you can have P and Q, because that's fine. Because you're keeping it private, basically. You're not sharing this with anyone. And actually, the certificates from OpenSSL are stored this way as well. We'll see that. All right, so the function takes the D exponent that we calculated, it takes P and Q, it takes the cipher, and then basically now it's going to decrypt it and print it back out to the screen. So let's see what we get, and then I just have a print done. So I'm going to do this. And now Claude Shannon is the father of cryptography. Does that make sense? Okay, that's how it works. Let's try this again with the secret key, which is actually what you would be using this for. So remember, we did something like OpenSSL, AES, and you encrypted a message, and we would put in a key. That's the key that you would encrypt here, and that's what you send. That's how you are able to exchange the key securely. So I'm going to go over and change the input. These programs are meant to use small things. You can have errors if you start giving it bigger files. Okay, so or big, longer text. So be aware of that. All right, so let's try a key. All right, so this is 1, 2, 3, 4, and then ASD, a few letters. So let's try it. And there it is. See it. So basically, this means that it took the information, it encrypted it, it generated a file, then it read the file and decrypted it. Okay, so that's the whole pipeline, right? That completes it. Now we're just going to go into the details of the algorithm and go from there. All right, so now let's take a look at the different functions that we have here. We have some utility functions just so that we can convert from like hex to integer, integer to list, string to integers, things like that. So those are there as well. We can just, look at them and see how they work. All right, so the functions will be get prime, gen RSA, and then we have our encrypt, and we have our decrypt over here. All right, so let's kind of navigate. All right, so the first function, we have some utility functions here. So print cipher text in hexadecimal. So we've done this a couple of times before just for convenience. We don't want to print these byte arrays. We kind of instead want to look at it as a hex, right? It's easier to move around sometimes. So this function is handy for that. It takes a list of ints basically as input. So we'll take a look at that one. Here's the decryption function. This one is a little bit different because it uses the Chinese remainder theorem. Just want to like think of it as an algorithm implementation. So we'll take a look at that as well. So that's the decrypt function. Here we have the encrypt function. This one is actually very similar to what we implemented by hand. So we'll just take a look at it line by line. This returns the lengthened bytes of the modulus, so the n. Then we have some utility functions, various utility functions like text to int, so convert a text string into an integer. So these are the things that, by hand we just had like 42 and then we converted it. So now obviously we have text, Claude Shannon. So we need to encrypt, convert that from text to int and then go from there. Then we have int to text, convert an integer into a text string, convert an integer into a list of small integers, convert a list of small integers into an integer, and so on. So then here we have gen RSA. So this is the function that actually allows us to get the parameters e, d, and n. All right, so we'll look at that. Inv, this function inv is the multiplicative inverse. So it's related to calculating d. So you can see here, it's the equation we talked about on Tuesday, d times e mod phi equal 1, if you remember, right? So remember that you're going to meet this equality, but how do you get that d value? So that's what this function gets you. And if you remember, I said that you're going to use something called the extended Euclidean algorithm for this. Okay, so we'll take a look at that as well. All right. And I think this is the last one, get prime, and that's it, right? So get prime is going to be a function just to get our prime numbers. All right. After that, we just have the libraries here, which are basic Python libraries. So let's take a look at the first one, gen RSA, and how that works. So let's go to gen RSA. So you can see, let's go to the main, right? So in the main, we calculate the 2 prime numbers with get prime, right? We got P and Q, and then P and Q are given to gen RSA, which gives us back E, D, and N. So let's go to gen RSA. Bless you. All right, so gen RSA is here. Gen RSA takes P and Q. So we already know that the public key is E comma N, the private key is D comma N. So that's what we need to get. You also need to think about the issue that you may need to exchange these keys, right? So if you have Bob and Alice, 2 students working together, Bob needs to generate a public and a private. Alice needs to generate a public and a private. Then they need to make those available, right? So that then one, let's say Bob can securely send a symmetric key to Alice, right? So how do you do that? Okay, you have to think about it. All right, so the first step, if you remember, in RSA was to take P and Q. So P times Q equal N, right? That's, and then phi is P minus 1 times Q minus 1. So you might remember that. Then basically, you need to look at N, right? So you look at N, and you're going to say, if N is less than 65, 537, E can just be something like 3. Okay, but usually our prime numbers are going to be really large, so I don't anticipate that it's going to be. And so in that case, we've already looked at N, right? For the P and Q that we have, and so it's pretty big. So then in that case, your E will just be 65, 537. So the public key is going to be 65, 537, comma, that N, whatever it is that we've computed. That's it. So that E is already calculated, N is already calculated, but we need D. That's the critical part. To get D, if you remember, that's the function I just told you about, inv, and inv will take E and phi, basically, as we discussed on Tuesday. So that should return D. So now we're going to go to inv, right? The inv function. And that's this one over here to get the D exponent based on this equality. So notice here that I have P and Q. Don't be confused by that. the parameters are E and phi. Okay, we follow the logic. This script actually, if we analyze it, starts here. It starts here. And it just uses this function xgcd, which is defined in this thing. So I'm not going to require you to, understand the Euclidean, extended Euclidean algorithm. I mean, it's an algorithm that was created pretty much to be a black box. But just keep in mind, if we look at the logic, what's happening here is we have P and Q. This function this function xgcd takes P and Q as input. So that means you go in here into this function, right? And it's looking for values that meet this equality, right? Through this algorithm, it'll return these three variables, x, s0, t0, of which we only need the first two, which are s and t. And it's going to assert that it's equal to 1. And then basically, it'll do this logic to return t. Okay, so that's basically, you can treat this algorithm as a black box if you'd like, or you can proceed and, print it. I encourage you to print every single little line in there and see what's going on. But it's an algorithm for calculating D, basically called the extended Euclidean algorithm. Any questions on that, guys? Yeah. All right, great. So again, as I said, by hand, we were talking about this. I basically had to, I always had to tell you, okay, D is going to be this, right? And then you guys would plug it in, and yeah, it was equal to 1. But we need, obviously, a practical way of getting D, so then we need to use this algorithm, which helps us to discover the appropriate D. All right, so if you notice then, in should return one value D. So then if we go, we scroll down to gen RSA, it does in fact, right? So we invoke in, we give it E and phi, and it gives us our D, and then we have now our E, D, and N. Any questions? So a more important thing to consider, I would say, for the homework is that each of you needs to run gen RSA. Like, let's say, it's two students, Bob and Alice, are working together. They want to send a message securely, right? They'll use AES. They need a secret key. So that's encrypted. So the message is ready. You send it, but then the AES key needs to be sent. You're going to use RSA for that. But you need to use, if Bob is sending the key to Alice, then Bob needs to use what? Bob needs to use, to achieve confidentiality on that key, Bob needs to do what? Oh, yeah, please. Yes, exactly. Because Alice then will use her private key to decrypt it. Does that make sense? So that's the key thing that you need to get right for this assignment, problem 4. Okay? Any questions on that? So how are you going to exchange the public and the private key? That's up to you. All right. You already know here, we've already seen that we can print them, right? So when you run gen RSA, I even created this public and private, right? So you'll keep this one private, but you can share this one, right? And then this needs to be used by the other person. Okay, so I'll give you some time today to work on this exact problem, right? And this is the first time that you're doing this exercise, I think. All right, so yeah, so that's the basic logic. So we will, we've done the gen RSA, right? So we have the public and the private key. Now, the next thing that we should look at is the encryption, right? So encrypt is actually very similar. I know that this is the function for encrypting. I know it looks different from like just the equation I gave you, right? So this should correspond to what? This is encryption, so it's M to the E mod N, correct? That equation. And it's this is the implementation of that. If you notice, key things to look at. So this is the message. So in a loop, you're iterating through it. And you can see this here, this is like the key thing to look at. How just means it's a Python function. There's several ways of doing this, but this is a convenient Python function which allows you to take something to the power of and then do the modulus operation. So it does everything for you, basically. Okay, so here we have the message, the plain text, I should say, the E exponent and the N. And so you're going to encrypt the message here. Obviously, you're iterating through the text as a string. You're going to do several checks of length and things like that. And then you're grabbing the text and you're converting it from text to int with one of the utility functions. Okay. And then once you have it, it's called AUX1. This is an assertion just to make sure it's, it meets certain conditions. And then here, that's your plain text, the key, the mod that creates AUX2. And then we're just going to take that AUX2 and do an int to list. That's one of the other utility functions to create that list of integers, basically, that you guys saw. And then basically, that's your output over here, which you return. Does that make sense, guys? Any questions? Yeah. And as I said, I encourage you to print every, debug it, right? Print every line just to get a better understanding, but that's the basic logic of it. So you're sort of iterating through the text there. All right. That gives you the encrypted version, and then we have the decrypt. So the decrypt is a little bit different from what we did before. If you notice, instead of doing C to the D mod N, here you're doing two POWs, if you will. That POW is the function that was doing that, right? So one POW, so because N, what is N really? N is P times Q, right? So but if you notice, this is doing, instead of taking N, it takes P and Q. So you're just doing that POW for P and that POW for Q, basically. So this is a more detailed implementation of the decryption. But in essence, the same idea. You're going to take the C text in this case, list to int, right? And then that AUX3 gets raised to the power here, right? And then creates M1 and M2. And you combine these two to finally create you can see that here. And then finally you get your output, which is the decrypted message, basically. Any questions? So that's, the decryption process with this function. So for a lot of these, you can just treat them as black boxes, but at the same time, this is a full implementation of RSA. Like there's nothing, everything is written from scratch. And this is as deep as we're going to go with RSA, but you can dig deeper if you want by just printing everything line by line. Got it? I'm not going to ask you to write this function like this on the exam or anything like that. Okay. So we're going to stick to what we've been doing on Tuesday and the equations, basically. All right. So that should be everything. So that's encrypt. I mean, I leave the print, the int to list and whatever to you. Those utility functions you can check on your, on your own, all of these. And then finally, I want to show you the get prime, which is an interesting function. So you guys, maybe I'll let you read through it and you guys tell me what you think is happening, right? So just as an exercise. So let's take a look at get prime, right? So we have an N. What is N? 256, 1024, something like that, right? So we get an N-bit pseudo-random prime. Okay. So pseudo-random, that nothing can be random here. Why is it pseudo-random? Because we use this function called get ran bits N. What is get ran bits? From random, import ran range and get ran bits, right? So we're trying to get a random sequence of bits. And so that's the first step, right? So according to this algorithm of this size, we get that sequence P. And then what do? We just have a nice little loop that says, while not is probable prime, keep repeating it, right? So get another get ran bit. So it's literally like randomly, right? We're creating sequences of bits and we're hoping that one of them is what? Prime. And then once we find it, we just use it. So notice, what is this function? Is probable prime. So that's defined up here. Define is probable prime. And so this is the Miller-Rabin primality test. So again, outside the scope of the class, some very intelligent people created this algorithm, right? But yeah, we're just going to use it as a black box, basically, to check that these things are primes. So this function itself is what? It's a for loop. If you notice, it does a for loop. And during that for loop, you're running another function called is composite. And this is going to be defined here is composite. Check if n is composite. So apparently, if it meets those conditions, then that would be a prime number as defined by this Miller-Rabin primality test. Got it? So that's how you can get a prime number. All right. But anyway, you can treat it as a black box if you want and just trust that this is giving you some prime numbers. All right. So that's the entire RSA algorithm, as you can see. And the rest, I would say, are just technical things in Python if you're a really good coder of how to do things efficiently. So I will summarize again then. So we have, you're going for your homework assignment, you're going to try all these different seeds. And this might take a while, right? One of these, especially the 4096. I think, that might take longer. The other ones I think are pretty quick, are quick enough. You'll generate your two prime numbers, P and Q. You will remember that even though I wrote Claude Shannon is the father of cryptography, kind of as an illustration, RSA is mainly for key exchange and not for message exchange. So if I ask you in some exam, send a message securely, you really should not use RSA for the message, right? You should use something like AES for the message, and then obviously AES needs a key. That key should be exchanged via RSA. Okay. All right, so then you generate with P and Q, ED and N, that makes up your public and private key. And then you can just use the functions encrypt. I provided the files to take the cipher and use pickle to create a file that you can send to your classmate. Now, the key question that you need to figure out is, how are you going to exchange the keys? Do you see this? Like, I have not solved this part. And I'm leaving that to you. It might be easy, or it might be a little bit not so easy, right? So think about that problem. All right. But yeah, that's basically RSA. Are there any questions? And I've provided several helper functions in here. Notice, for instance, there's this print hex list, etc. So that's basically the RSA algorithm. Questions? Clear? Everything's clear, guys? So hopefully it should make sense, right? It's what we did on Tuesday. I will come, we still have at least another lecture on RSA like the one we had on Tuesday. That would have been next Tuesday, but of course we have full break, so it's going to be delayed a little bit, right? And we'll go back to solving more problems by hand, but hopefully it's clear that what we're doing by hand here, this is the Python implementation of it. All right, so let's just try one more time. I'm going to use a bigger size. So instead of 256, I'm going to try, let's say 1024. That's a good number. Okay, Control X, Y, enter. Clear. It's taking a while. Oh, there it is. So it finished, right? So the whole process has been done. So yeah, it's kind of fast. All right, so that's problem 3, I think. So we can go back to Brightspace and take a look at the Word document, right? So let's make sure that I'm pretty sure we've completed problems 1 and 2. We did those last Thursday. Now problem 3, I think we just completed it, but let's read it. So now that you have completed problem 2, try using a more advanced implementation. Because of the complexity of the RSA algorithm, some functions are provided to you, which, what I just described. For this problem, you will need the source code provided, on the GitHub. You will need to write the generate keys function, which I've done. And then you need to use all functions available to generate the prime numbers, generate the keys, and encrypt and decrypt a message. Done, right? Okay, so that's problem 3. So just, run it. And then the one thing you have to add is change the length of the prime numbers and try those out for your lab report. So the last problem, this is what you now have to do with your partner. So I encourage you in the rest of the class today and the remaining, 34 minutes or so, work with your partner and try to send them, take a message. So now you need to create a text file, write on it something like, Claude Shannon is the father of cryptography, use OpenSSL or something, AES, right? You need to pick a key, encrypt that text file, so you'll generate a cipher of it, right? That's the message. You can go ahead and send that message via email and just that to your partner, but you still have the second problem of you used a key, right, for OpenSSL AES. So now that key needs to go into this, right? It needs to go here, and you need to encrypt that key so that you can exchange it securely. So the key thing, though, the key problem is you'll need to decide, you need to figure out basically whose public key you need to use and how you're going to exchange that. Does that make sense? Any questions? So yeah, so please work on problem 4. Yeah, go ahead. Yes, exactly. No, that's what I'm saying. So we need to do this correctly, right? So the correct way of doing this is that each of you now needs to have your own public and private key, right? So whenever you're using asymmetric encryption now, Bob needs to create her public and private. Alice needs to create her, his public and private, and then you can send the public key via email if you want already to your partner, right? And then they can use that. They need to find a way to use that public key in the code, right, to encrypt the message. So if we look here, if you're just going to encrypt, you need what? The plain message and E and N. So that E and N, right, if you're Bob, comes from Alice. Do you see that? And then once Alice receives the message, she's going to use decrypt. So this is the message she received, and she's going to use her private key, which is D, P, comma, Q, right? Because P times Q is N. Got it? That's it. So work on it. Okay, and raise your hand if you have any additional questions.
No, no. Yeah, decrypt. Oh, 9 first. Yeah, just a little bit. Yeah. It's fine, unless it's